Okay, so let's see. So last time I started talking about Dehn's surgery on knots in the three-sphere, and I guess I explained that there were three kinds of knots. There are torus knots, satellite knots, and hyperbolic knots. And the fibered space complements correspond to the torus knots, the toroidal knot complements correspond to the satellite knots, and everything else is hyperbolic. So generically, you know, your knots is hyperbolic, and we can give a pretty complete account of what happens when you do a Dehn surgery on either a torus knot or a satellite knot. And so the question is, what about hyperbolic knots? So this is the generic case, and so I want to talk a little bit more about what seems to be the picture here. So the goal, the goal is to not break the chalk quite so soon. All right, is to you know, sort of completely describe. Let's put it this way: all you know, all sort of K alphas such that K is a hyperbolic knot. K is a hyperbolic knot in the three-sphere, and K alpha, the Dehn surgery corresponding to whatever the slope alpha, you know, is non-hyperbolic. So this is what I was calling the you know, exceptional slopes. So that's the goal. So I mean, I pointed out, I guess I mentioned what happens with a figure 8 knot. You get these 10 exceptional surgeries, these non-hyperbolic surgeries. 0, of course, always 1 over 0, but in the figure 8 knot you get 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, and you know, I think it's kind of surprising that you think, well, this is the simplest hyperbolic knot you can imagine, and already there's a whole bunch of non-hyperbolic Dehn surgeries, and so probably, you know, the whole thing's a bit of a mess. You can probably get very many, you can probably get complicated knots that have lots of non-hyperbolic surgeries. But in fact, again, as I mentioned, in fact, the figure 8 knot seems to be the worst possible. So, in other words, the more complicated the knot, it seems to be the fewer exceptional surgeries you seem to get. And so that's what makes it sort of possible, perhaps, to, you know, think of achieving this goal. Anyway, so let me now begin to spell out in some more detail. You see, if you have, so I'll always be thinking about a hyperbolic knot in S3 now. So K will always denote a hyperbolic knot in the three-sphere. And so let's just recall, you know, in view of what I said in the first 2 lectures about, you know, about the structure of 3 manifolds, if you've got the closed 3 manifold K alpha, if it's not hyperbolic, so what can it be? So let's just list it. You see, K is either. So, well, of course, one thing it could be, so let's dispose of this right at the beginning. It could be a counterexample to the geometrization conjecture. You know, so maybe this is proved, maybe it's not. It doesn't, whatever. It doesn't really matter. But so this could happen. And obviously, we're not going to discuss this any further. But if you assume the geometrization conjecture, then I guess I can write some more up there. Again, in view of what I said about the classification of 3 manifolds, I mean, okay, so it could, for example, be, it could be reducible. Okay, it could be not irreducible. So, so in other words, it could either be S2 cross S1. So maybe it's S2 cross S1. Obviously, that's not hyperbolic. Or it could be a non-trivial connected sum. So it could be non-prime. Okay, so that takes care of the possibility that it's reducible. Well, another possibility, it could be the 3C. See, if it's irreducible and you're assuming the geometrization conjecture, then either it's and it's not hyperbolic, then either it's a Seifert fibered space or it's toroidal. Well, so what are the Seifert fibered spaces? So it could be S3, which is a sort of rather trivial Seifert fibered space, or it could be a lens space. So this would be a Seifert fibered space with base, surface, a two-sphere, and two singular fibers, or it could be what I call a small Seifert fibered space, which is I mean, it's not as small as this one, so it's a smallish Seifert fibered space maybe. But, it's you know, a Seifert fibered space over the two-sphere with three singular fibers. Okay, so remember that's what so over S2, three exceptional fibers. And so again, if it's not that, then it would have to be toroidal. It would have to contain an incompressible torus. So again, I want to emphasize that, you know, we know this, that these are exactly the possibilities. Okay, for any closed manifold that's not hyperbolic, then it has to be one of these. Okay, so let's just see in the context of the manifold you get by Dehn surgery. So let's just go through. Could you get S2 cross S1? Well, there's a famous theorem of Gabay that says no, you can never do that. So this never happens. So this was the so-called property R conjecture, and this was proved by Gabay in sometime the mid to late 80s. So if you take any non-trivial knot, it would have to be zero surgery just for homological reasons if you were going to get S2 cross S1. And in fact, you never get that. So that's good. Well, what about a connected sum, a non-trivial connected sum? Well, case hyperbolic. This is conjectured to never happen. So this is a conjecture of Gonzalez Acuna and Hamish Short. So this is equivalent to the so-called cabling conjecture, which I won't spell out. There are two people here. All right, so there we are. That's it. And so this is supposed to never happen, and this is an open problem. So I won't even assign this as homework. I mean, if you want to turn it in, that's good. But so that's a nice problem. What about, okay, so the third possibility, what about S3? Well, of course, the trivial surgery 1 over 0 gives you S3, but it never happens non-trivially. So this also never happens. And so this is equivalent to the knot complement sort of conjecture, whatever. So this was proved by John Lukey and myself a while ago. And there's a new proof, just quite recent, by Osvath and Szabo. So in these first three cases, well, again, even the geometric translation conjecture, I mean, that's conjectured never to happen. This is conjectured never to happen. The other two are known never to happen. So what's left? Well, there's lens spaces, small Seifert fibered spaces, or toroidal manifolds. And they do happen, in fact. So 4, 5, and 6 do happen. So let me describe an example. So if you take K to be, this is rather a famous knot in this context. It's the -237 pretzel knot. And it's also sometimes called the Finterschel-Stern knot. And well, here we can easily draw it, right? I mean, it's so you see the -2, 3, 7. I hope 1, 2, 3. That's just about right. So that's this knot. So this is a hyperbolic knot, and I mean it's not a torus knot, and it's not a satellite knot, so it has to be a hyperbolic knot. And I mean one can actually, I mean, well, so it turns out, I mean this is really a beautiful knot because it simultaneously illustrates all possibilities 4, 5, and 6. So it's really nice. So what happens here? I mean, again, one can compute this. Well, I mean, one can. The exceptional slopes for this knot, in other words, the slopes that the surgery slopes that give you non-hyperbolic manifolds are precisely, well, of course, there's always 1 over 0. The others are 16, 17, 18, 18 and a half, 19, and 20. And I always think there's a nice bit of numerology here. You know, I think it's great if you take the symbols minus, 2, 3, and 7 and rearrange them, you get 3, 7, 2. And so that's so there's no excuse for not remembering. Makes you think, doesn't it? Eh? Mm-hmm. So. Yeah. So again, I mean, like I said, obviously, you know, so what do these guys correspond to? Of course, this corresponds to S3. Fintischel and Stern, a long time ago, pointed out, noticed that these two, 18 and 19, they actually give you lens spaces. So not only do you get one lens space, you get two. You get two lens spaces, and 16, 37 over 2, and 20, these manifolds are toroidal. They contain incompressible tori. And 17 is a small Seifert fiber space. It's a Seifert fiber space over the... In fact, it's one of these spherical manifolds. In fact, it's spherical. So it has finite fundamental group, spherical of icosahedral type, 2, 3, 5. In fact, the fundamental group is it's a binary icosahedral group, right? Cross. Well, it has to be Z17. See, because we know the homology is if it's 17 surgery, the homology has to be Z17. So this is really a beautiful example. I mean, it illustrates all the things that can happen in one knot, And well, to see this, I mean, you have to do some sort of computation. The easiest way to do it is to look at the so-called tangle sort of pictures, and I was hoping to, draw some transparencies at some point and perhaps show that, but maybe I won't. But anyway, one can actually see this, see these exceptional surgeries quite directly. Okay. Well, one thing you must have noticed about this, let me also recall that for the figure 8 knot, I wrote this up last time, right? Remember it's the E of the figure 8 knot. Again, what was it? It was plus or minus 1. Oh, 0, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 4. Well, so you must have noticed that these numbers are almost all integers, right? So why are they all integers? I guess there's one that isn't, but it's almost an integer. So what's the point? Well, what's the point? The point is this. Remember that I sort of indicated that, if you think of just the more general context of Dehn filling, where you start with a hyperbolic manifold M, let's just say it's got one torus boundary component or something. If you do two Dehn fillings, right, M alpha and M beta, that represent some kind of degeneration of whatever probability, then the intersection number, delta, between these two guys has to be rather small. So in particular, if you have a hyperbolic manifold, if this is not hyperbolic, then that should imply, I mean, as I say, it's perhaps not immediately clear why this should be true, but it turns out to be true, and you can, one can sort of prove that anyway. But the intersection. And so notice that, of course, if you have a knot in S3, right, see K1 over 0 is always S3, right? And notice also that what's the distance between M over L, the intersection number between this and the meridian? Well, of course, it's just L, you see. And so you expect L to be small because because we're talking about knots in S3, there's always this trivial Dehn filling that gives you the tree sphere, which is non-hyperbolic. And so any other non-hyperbolic filling should have intersection number small with, so we expect L to be small, but if, we have no right to expect it to be this small. But so it's kind of amazing. So in all known examples have L equals 1 or 2. And I'll say a little bit more about that as we proceed. Okay. Okay, so let's see. So we decided that there are three things. There are three things that can happen. You could get a lens space, or you could get a Savage fiber space, or you could get a toroidal manifold. So let's just discuss this. So what's known about this? So what happens if you get lens space? Well, so let me give you, in terms of the construction that I described last time, let me give you a description of how you can sort of construct knots that have Dehn surgery to give you lens spaces. So here's what you can do. You can start with a genus 2 handle body, W, and let's take a curve K in the boundary of W, okay? And so let's choose, we want to add a 2 handle. Remember this square bracket notation I was using to mean you take W and you add a 2 handle along K. I'd like this to be a solid torus. And so here's my handle body genus 2. Let's indicate the two sort of meridian discs here. Knots were blue, I seem to remember. So here's obviously if I had a 2 handle along this, I just get a solid torus. In fact, it's actually sort of convenient to think just in terms of the fundamental group. You want to get something with fundamental group Z when you kill K. And in fact, you can prove that that's equivalent to getting a solid torus. And you can prove that getting Z is equivalent to saying that K is primitive in W, i.e., this means that K represents an element of K belongs to a free basis for pi 1 of W, which of course is a free group of rank 2, right? So in fact, in some sense this is perhaps not that important. We just want knots such that you get a solid torus. But in fact, you can easily check that if you. It's equivalent to saying that K belongs to a free basis. I should say that handle bodies are very deceptive. If you haven't thought about handle bodies before, it's easy to think that they're very simple objects. So I've drawn a very simple primitive element. There are 2 disks. And here's a knot that intersects one of them once and is disjoint from the other one. Well, that's equivalent, in fact, to K being primitive. But the picture can be very, very much more complicated. Up to homeomorphism, the picture has to look exactly like this. But if someone gives you a handle body with a given pair of meridian disks, then there are many very complicated looking curves. The point being that there are many very complicated looking pairs of meridian disks. And so you have to beware that the picture can look much more complicated, although up to homeomorphism it really is just that. Okay, and so what's the point here? So now, you see, now what I want to do is go into S3, and suppose we've got so let F be a genus 2 Heegard surface in S3. So that means that S3 is just decomposed into 2 handle bodies of genus 2. Okay. And suppose I can find a knot K that lies on that surface. Well, in this construction I'm about to describe is due to John Berge, so one says that K in F is a Berge knot. Well, if and only if it's primitive in both handle bodies. So K is primitive in W1 and W2. So there are in fact infinitely many, well, until you look at this in more detail, perhaps one doesn't appreciate how complicated this can be, but there are lots of such things. I mean, there are infinitely many such. And in fact, they've been completely classified. This is the amazing thing. But by Berge, they're completely... I mean, he actually lists, I think it's 12 infinite families. They're just parameterized by certain integers. I mean, you take a standard picture of a genus 2 Heegard surface in F3, and you've got this curve that kind of winds around in a complicated sort of way. And he completely figured out all such curves that had the property that they represented basis elements on both handle bodies. So they're completely classified by Berge. So again, I want to really emphasize that this is an explicit list, well, what's the point about this? You see, but this sitting in the surface determines, as I said last time, it determines this sort of slope, this integral slope m, just by looking at the framing of the knot that it picks up from sitting on the surface. And as I explained in the last lecture, if ever you have a knot in S3 sitting on a surface and the surface splits the S3 into 2 pieces, W1 and W2, whether they be handle bodies or not, then when you do the M surgery, I went to described this in some detail last time, and when we applied it to what happens when you do PQ surgery on a PQ torus knot, and we saw you got to connect some of 2 lens spaces. There, W1 and W2 were genus 1 handle bodies. So this is somewhat analogous. Well, what was the general principle? The general principle was that you get, it's simply the result of adding a 2 handle to W1, union along the boundary of what you get by adding a 2 handle to W2. Okay, so that was the general thing that I explained last time. Well, but you see, we've chosen K so that this is a solid torus, and this is a solid torus. Well, what do you get if you glue 2 solid tori together? Well, you get a lens space. I mean, you could get S1 cross S2, or you could get a 3-sphere S3, but we know that you don't in this case, right? Because, we know that you never get S3, or, if the knot's non-trivial. So this is Berge's construction for getting knots that give you lens spaces. And as I say, there's this completely sort of explicit list of them. It's quite a complicated list. There are these several infinite families. And the Berge conjecture, the conjecture in this is that these are the only things. So if K a knot in S3 such that K M is a lens space for some integer m, then that should imply that K is a Berge knot. So these are the only ones. These are the only. This is the only show in town, probably. Okay, so this is a... Does the Berge conjecture also cover non-integral surgeries, or just... Non-integral surgery?
Well, so this is if you have a knot which has an integral lens space surgery.
Oh, great. So, right. That's just the right question. Eh? This man's wonderful. All right. I'm glad you asked that.
You can pay me later.
No, I've never seen him before either. That's amazing. All right. Yeah, right. So as Saul rightly points out, you know, you see, whenever you do this construction, you know, you take some knot on some surface, blah, 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 you know, it's always integral surgeries we're talking about because the slope that we're doing is always a slope that's picked up, you know, to get this formula, right? Which again, I'll give another application of this in a minute. We need, the slope is the integer that's picked up by the knot line on the surface. And so you say, well, what about non-integral surgeries? But luckily, see, in this case, there's actually a theorem that says that you never get lens spaces by non-integral surgery. So there's the cyclic surgery theorem. So this was proved by, gosh, I'll just call it CGLS, something in 1987. Work with, John, Culler, Lukey, Shalin, and myself. We proved that if, so again, if you've got M, let's say, well, M an irreducible, orientable, irreducible compact, orientable three-manifold, we've got a torus boundary component, blah, 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 and such that you've got two Dehn fillings, M alpha and M beta, if, oh, I should say, hang on a second, yes, sorry, not a Seifert fibered space, right? You see, first of all, right, I mean, remember, we discussed the Dehn surgeries on torus knots last time, and in particular, remember, we showed that if the distance, delta, from the surgery slope, M over L, to the fiber slope, PQ, if that was 1, then you're going to get a lens space, you see, because you're just going to get two singular fibers. And so you do get infinitely many non-integral surgeries. I mean, the denominator can be arbitrary there. They give you lens spaces. So we've got to stay away from Seifert fibered spaces. But the theorem says that if you do stay away from Seifert fibered spaces and you have two fillings, M alpha, M beta, that have cyclic fundamental group, then in fact the intersection number, delta, between these two fillings is at most 1. You know, so either it's alpha is equal to beta or they intersect exactly once. And so see a corollary of this, because S3 has cyclic fundamental group, right? If you have a non-Seifert fibered knot complement, in other words, if you have a knot that's not a torus knot or the trivial knot, I mean think of that as a special case. So immediately we get this corollary that if K is a knot in S3, not a torus knot, or the unknot. I mean, then if K M over L is a lens space, that implies that L has to be equal to 1. You see, because remember, as I pointed out a few minutes ago, L is the intersection. It's the distance delta between that slope and the meridian 1 over 0. And so 1 over 0 gives you a cyclic fundamental group. And so there you are. So in this context, we don't have to worry about non-integral surgeries. And so the Berge conjecture, should cover everything. Again, once we've taken care of torus knots, which we already have. So, okay. So that's the conjecture there. Let's see, I was going to say something. Oh, wait, what was I going to say? Right. Notice also, of course, that the cyclic surgery theorem in this context says that if you had two Dehn surgeries that gave you lens spaces, well, they have to be integers by this theorem, and their intersection number would have to be 1. In other words, the distance between them would have to be 1. And notice that the minus 237 knot does in fact have two lens space surgeries, 18 and 19. So that's good. I mean, 18 and 19 differ by 1, which is what the theorem says that they have to. So again, that Finterschel-Stern knot illustrates, it illustrates the sort of worst that can happen in many, many ways. So let me just say, So this Berge conjecture, I think, is one of the main problems in the field. Let me just mention, I'd say that, Osvat and Sabo, in their work on Peter has just arrived in time to have his name mentioned. What timing, yeah. So, no, so I mean, with their Heegard floor homology, they've got some very interesting results on this Berge conjecture, which maybe they'll talk about. And in particular, I mean, a very good theorem of theirs is that, again, this was mentioned by Zoltan, that K, well, if it's not the unknot, then you never get RP3, So that's in fact a sort of special case of the Berge conjecture, if you like. I mean, okay, so that's sort of that's the picture for lens space surgeries. We have this infinite family of knots that do give lens spaces, but they give lens spaces because they were precisely designed to do that, and they appear to be all. So that's a very clear kind of picture. It only remains to prove it. Okay, what about Seifert fibered spaces now then? So let me talk about Seifert fibered spaces, I mean, they're not lens spaces. I mean, so maybe I should say other. Let's talk about other Seifert fibered spaces. Again, like I said, I mean, they're either toroidal, in which case we might discuss that separately, or they have to be sort of small, but let's kind of discuss them in general. So, well, once you see Berge's sort of construction, you can see that, that you can do a similar thing for Seifert fiber spaces. So again, suppose W is a genus 2 handle body, and let's suppose we've got a curve K in the boundary. So let's say that's Seifert fibered, right? If when you add a 2 handle to the handle body along K, you get a Seifert fibered space. So, well, we want to get a Seifert fibered space with one boundary component. So I guess we'll take this as separating, a non-separating curve, let's say. If WK is a Seifert fibered space, and actually, I think this is true. I think the only Seifert fibered spaces that you could get in this way would have, there are sort of 2 classes. The most common thing, I mean, is that you'd have base, the 2 sphere, the disk, base the disk, and 2 exceptional fibers. Or you could have, there's another case which is sort of interesting actually. You could have base the Möbius band. You see that the base surface can be non-orientable even though the total space is orientable. You could have a Möbius band with 1 exceptional fiber. And there are examples of this. So let's call the curve Seifert fiber. Well, anyway, so let me just draw a very simple example. I mean, this is not perhaps that relevant, but again, again, there are infinitely many such things. But I mean, you could take a curve that perhaps goes twice round here and goes sort of 3 times round here. Well, okay, and then just sort of, that's a very simple example. And I mean, if you read off the fundamental group of the resulting manifold, you see that it's generated by 2 elements x and y in a single relation x squared equals y cubed. Well, you'll recognize that as the fundamental group of the trefoil knot. And in fact, you get the trefoil knot complement, which is a Seifert fiber space, over the disk with 2 exceptional fibers of multiplicities 2 and 3 when you do that. Well, now, okay, but now, of course, we want to put this into S3 in the same way that we did for the Berge knots. Oh, I could have left this up. Okay, sorry. So F is a genus 2 Heegard surface in S3. So there we are. So we go back to so again, there's going to be some slope m determined by this. But we say, so let's say this is a Dehn knot. These were discussed in the thesis of John Dehn, that if K is, you know, it's Seifert fibered on one of the guys, it's Seifert fibered on W1, and it's primitive, you know, on, I don't know, on W2. Okay, and again, there are certainly lots and lots of such things. I mean, there are infinitely many such. But a problem here, so let me just mention this perhaps as a problem, is to classify them somehow. I mean, so here's, actually, I mean, Berge, I think, is working on this as we speak, so maybe this will be done sometime in the not too distant future. But one would like a sort of complete description of such knots, just in terms of, you know, there are probably going to be lots of infinite families, but hopefully not too many, and, you know, it's reasonably organized, just like it is with the Berge knots. Anyway, if you're given such a thing, then again we can go over here, you see, and if you do M surgery on such a knot, then by the way this was set up, you get this, which in this case, you see, we chose K to be Seifert fibered in W1, so that means that this is a Seifert fibered space. And now you're gluing onto that a solid torus, because it's primitive on the other side. Okay, so this will be a Seifert fibered space, basically. Okay, I mean, let's say this is usually, I don't want to get into, you know, it's usually going to be a Seifert fibered space with, again, there are going to be two cases. I mean, again, it's usually going to be, in the first case, you see, you're going to get base the two-sphere and three exceptional fibers, again, generically. That extra solid torus you glued in will give you another exceptional fiber, or you can get the Möbius band, the projective plane rather, when you could, and two exceptional fibers. Now, as I say, usually, because, you know, you might just get two exceptional fibers, so in other words, you might just get a lens space. If you're really unlucky, you'll actually kill the fiber, so you'll get a connected sum of two lens spaces, right? And so on and so on. But, you know, basically, this is what you'll get. So this is a source of many knots that give you Seifert fibered surgeries. Okay? So let me point out that if you have two exceptional fibers and base surface P2, any Seifert fibered space of this type contains a vertical incompressible torus. Right, I mean, because, you know, here's, well, I don't know how to draw P2, but I mean, it's something like that, you know. And then you have two exceptional fibers. If you take a curve like this, that curve does not bound a disk on P2, you know. Well, I mean, it does, but the disk that it bounds contains two exceptional fibers. So when you lift up, when you take the inverse image of this curve, you get a vertical torus that does not bound a solid torus on either side. On one side, it bounds a circle bundle, a twisted circle bundle over a Möbius band, and on the other side, it bounds, you know, a Seifert fiber space over the disk with two singular fibers. So you get vertical incompressible tori. And there are actually such, I mean, you can actually, I mean, this case here does actually arise in this context of knots in S3. There's a rather small number of them. Again, there are infinitely many. But so one problem, so you can actually get toroidal Seifert fibered spaces by Dehn surgery on hyperbolic knots. And so let me just pose as the first problem to show that, you know, K hyperbolic, K, well, let's say Km, a toroidal Seifert fibered space implies that K arises in this way, right? K, well, K is as above. I mean, it's one of these Dehn knots, blah, 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 blah. Okay. So that would be a nice, and there, I mean, it's a relatively small sort of subclass of all the Dehn knots. I mean, this is by far the most common situation. And so anyway, so perhaps the natural conjecture here, just by analogy with the Berge conjecture, would be that if you have a knot, hyperbolic knot that gives you Seifert fibered space, by some integral surgery, then it should be a Dehn knot. Well, unfortunately, that's not quite true. So let me just briefly mention that there are some, more recently, there were some other examples discovered by Miyazaki, Mattman, Miyazaki, and Motegi. So Mattman, Miyazaki, Motegi. So they found it. So there exists, hyperbolic K with Km Seifert fibered space, not a lens space. Okay, okay. Well, let me just be explicit here. Okay, small Seifert fibered space. K not a Dehn knot. Okay, but again, you say, well, all right, this is looking a bit more complicated again. But in fact, there aren't that many examples. I mean, there are infinitely many, but they also all lie in a genus 2 Hayguide surface. It's just that. So why are they different? It's just that they're separating. They're separating curves. And so, I mean, the picture here is a bit more complicated because, I mean, the surgery slope m is clearly not visible then from this description because, if it's separating, then of course the induced slope would have to be 0. But so somehow the m is not really visible in this. But it is interesting that, again, these are rather small knots in the sense that they can be made to lie. I mean, sometimes people call these double torus knots. The torus knots are the ones that lie on a torus. The double torus knots are those that lie on a double torus. But anyway, so in some sense they're all very small knots. And so anyway, the natural problem here would be to show that, is, so if K hyperbolic Km Seifert fibered space not a lens space, is K either a Dehn knot or a Miyazaki, Motegi, Mattman, Miyazaki, Motegi. So in particular, you might want to show that, at least show that the knot can be isotoped onto a genus 2 Hayguide surface. Again, let me just finish this discussion of Seifert fiber spaces by addressing the point that Saul raised in the case of lens spaces. These all talk about integral surgeries, or at least, most of them do, because that's. So what about non-integral surgeries? Well, again, there's no analog of the cyclic surgery theorem known in this context. I think this is a really important problem. I think to show that K hyperbolic and K m over L Seifert fibered space implies L is equal to 1. So that's I think a major problem. I mean, it's known for lens spaces, as I said, but that's what one needs to show here. The Seifert fibers case. Okay. Okay, so I've kind of discussed lens spaces, other Seifert fiber spaces. So what's left? Well, there's the toroidal case. Well, as I mentioned, I mean, there's a slight overlap because I've already described that you can actually get toroidal Seifert fibered spaces, but let's now discuss the toroidal case. So hyperbolic knots, some Dehn surgery that gives you a manifold containing an incompressible torus. So that's the last case. And here there are sort of two subcases I want to distinguish. The first would be where L is greater than 1, where you have a non-integral surgery. Now we remember that this can happen. Remember the 37/2 surgery on the -237 pretzel knot actually is a toroidal manifold. And so again, so this is the case in which we actually do have a complete picture. So there exists a very explicit, again, sort of explicitly parameterized infinite family of hyperbolic knots K, such that K m over 2 is toroidal, for some m. And so this family was described by Udavi-Munoz. And so I'll call them the Udavi-Munoz knots, or EM knots. So again, there's this explicit infinite family, including, of course, the minus 237 pretzel knot. That's the smallest, the simplest, the first one in this family. Let me just mention that in fact what do you get? What manifold do you get? It turns out that again, the toroidal manifold, it's actually in some sense the simplest kind of toroidal manifold you can sort of imagine. It's just two spaces glued together along a torus. This is a torus. In fact, that's your incompressible torus. And M1 and M2 are actually Seifert fibered spaces. So it's a Seifert fibered space over the disk with two exceptional fibers. So they're all of this rather simple form. And again, let me also mention that these are the only examples known. So these are the only examples known of K hyperbolic and K M over L non-hyperbolic with L greater than 1. So these are the only known examples of non-integral, sort of exceptional slopes. And again, so let me also mention that the EM knots, they also lie in a genus 2 Heegard surface. So they're also double torus knots. So there's something, all these examples that are known are sort of fairly simple. Well, now this is the one case in which we do have a complete picture now. So there's a theorem, which I guess John Lugie and I proved. It actually appeared just less than a week ago. So that in fact these are the only knots. So if K is a hyperbolic knot in S3, and you have some non-integral surgery that gives you a manifold with an incompressible torus, then in fact L is equal to 2. It's a half-integral surgery, and K is a Udavi-Munoz knot. So somehow this was the result that it makes one think that perhaps it's not beyond the bounds of possibility that eventually maybe you can completely describe all non-hyperbolic Dehn surgeries on hyperbolic knots. So so this case is completely this case is completely understood. We have this very explicit family. They're actually, in some sense, they're really two infinite families, each one parameterized by 3 integers. It's a very explicit, very, very beautiful set of knots. They're quite complicated, but again, they're constructed with this property in mind, and so in another sense, they're actually quite simple. And they're the only ones. Okay. Now so the one remaining case would be where you get a toroidal manifold by Dehn surgery, but it's an integral surgery. Now again, we can use, we can use our standard trick of taking knots on a genus 2 Heegard surface. I'm sorry? Oh, okay. Oh. Right, sorry. Okay, Well, so here there are many examples. And so again, just using the philosophy that we've been espousing in this discussion, for example, you can take, you could take K to be some, let's say, non-separating curve, in our favorite genus 2 Heegard surface, right? such that, let's insist that F minus K is incompressible. So F separates S3 into these familiar two handle bodies of genus 2. So let's suppose that obviously F itself is highly compressible into W1 and W2, right? Because they're handle bodies. So, but if you choose K to be sufficiently complicated, I mean, this is the generic case. People call it disk busting. If K hits every possible compressing disk, so it's easy to figure out what that means. I mean, you can express it algebraically as well. It means, well, okay. But let's just suppose it's incompressible in Wi. I equals 1 and 2. And so again, this is, I mean, if you draw a sufficiently complicated curve, it'll have this property. Well, then what happens, again, this picks up some slope m from lying on the surface. And again, let's write up our favorite sort of formula here. The M surgery then is going to be the result of adding a 2 handle to W1 along K, union along the boundary. So this is going to be this torus T, W2, 2 handle along K. And it's pretty easy to see, I mean this is the sort of thing called the handle addition lemma. It's easy to see that this condition star actually implies that that T is incompressible in Wik. I equals 1, 2. And so you get, so therefore T is an incompressible torus in Km. So here you get lots of integral surgeries. I mean, this is just one source of things that give you manifolds containing incompressible tori. Well, all right. I mean, being optimists, we say, well, maybe this is the picture here too. I mean, maybe all toroidal surgeries. I mean, by analogy with the previous discussion, for length spaces and so on, maybe this is it. Well, unfortunately, that's not quite true. In fact, let us note that in this construction, see, remember how we did this? Let me draw a picture that I had last lecture. When we add the surgery solid torus, so remember Km is M, the knot complement union V. V is the solid torus. And remember when we had this picture of K lying in a surface which separates the 3 into 2 pieces, W1, W2, and so on, when we take a neighborhood of K on the surface, we get these two parallel curves, which I call alpha and alpha prime, right? And so I had this picture. And so they bound these disks, D and D prime. And if you think about it, you see, what is this torus T? I mean, remember, you're just adding a 2 handle to W1, let's say, along K. So T, in our old notation, I mean, it's F0. That's with the complement in F of a neighborhood of the knot K. Well, you see, K was a non-separating curve on a genus 2 surface, so this is a twice punctured torus, right? And then when you add the 2 handle, the boundary components of this twice punctured torus now get capped off with the disks D and D prime to form a torus. I mean, that's where the torus comes from, right? Think about adding the 2 handle. And so we see that this torus T in here, if you look at the core of the solid torus V that you attach, so you get this C, you get this knot in Km, C is equal to the core of V. So this is, in some sense, you do a Dehn surgery on K, now you get a new manifold with a new knot, and this, I'm calling this C. Notice that the intersection number, just by definition, you see, T in V just consists of these two disks, so it intersects this core in exactly 2 points. All right? So if your example came from this construction, then the incompressible torus that you get, or at least there would be one, that intersected the core of the surgery solid torus in exactly 2 points. However, John Oysenach, a few years ago, constructed examples with the following property. Let me mention that. So there exists hyperbolic K in S3 such that, actually his examples just were just for zero surgery, but you can kind of modify them to do some other surgery. But anyway, such that this is toroidal. Oh, okay, let's put it this way. So for all n, such a K is toroidal, but any incompressible torus T in this toroidal manifold intersects the core of the in at least n points. So that shows that these examples certainly couldn't come from this rather naive construction. So that makes this look kind of complicated. And I might also mention, seeing I have a couple of minutes, there's another theorem, again in this, due to Udavi Munoz and John Lukey, that says that, again, for all n, well, the knots that lie on genus 2 Heegard surfaces, their complements have Heegard splittings of rather small genus. In other words, their tunnel number, if people know what that means, has to be really quite small, 2 or 3 or something. Anyway, but Udavi Munoz and Lukey showed that for all n, again, there exists a hyperbolic knot K, such that Km is toroidal for some m, and the tunnel number of K is greater than or equal to n. And so let me just say that, therefore, so therefore K certainly cannot lie on a genus 2, well, if n is large enough on a genus 2 Heegard surface. In fact, it can't lie on the genus of such a surface would have to be, have to be arbitrarily high. Okay, so I guess these two theorems show that the case of integral surgeries on hyperbolic toroidal manifolds is definitely more complicated. I mean, there are many more examples in some sense, and they don't seem to be quite so easy to categorize. And so let me just leave you with, I think the problem here is rather vaguer. So let me just finish with this. So the problem for this case would be, well, I think first you have to formulate the conjecture. So formulate a conjecture about K hyperbolic, Km toroidal, integer. Well, so first formulate it and then prove it. So that would be the. So in other words, yeah. So it's really not clear what's going on in this case. But one would hope that there might be a good kind of description of what's going on here. Okay, that's all.